everybody. My research project this semester is kind of a combination of efforts from 3 different classes. It's all about determining the proper methods to use to generate valid data while performing malware analysis and research. Today, I'm kind of going to give a brief overview of malware analysis so that you can have some background to understand my research. Discuss some of the previous works in this area. So I based my paper off of another paper, and I'm also going to talk about that other paper a bit. And I'm going to talk about how I performed my experience or my experiment, how I selected data, created a methodology to analyze proper research practices, and tested this methodology on 35 research papers from various conferences. So to start, we're going to talk a little bit about what malware is, how to detect and analyze it, and briefly some challenges that come along with that. Malware, put simply, is a program that's specifically designed to disrupt or damage a computer system. And we're going to focus on about 8 types. So the first type, and the type of malware most people seem to recognize, is the computer virus. Just like a human virus, a computer virus, it requires a host to spread. It's self-replicating, and it needs a user to allow these actions to happen. The second one, in contrast, a worm, is a standalone computer program. So we had a lot of trouble with these in the early 2000s. They spread really quickly by exploiting like security holes or unpatched vulnerabilities, and repeatedly making copies of itself. This can slow down computers, fill up hard drives, congest networks, and make a lot of these things that are really important unusable. Trojan horse is a malicious software disguised as benign software. So it doesn't self-replicate or propagate like malware worms do, but they are the most common type of malware because they offer users something enticing, and that's usually for free. That's a process called social engineering, when you entice somebody and you can infect them later on after that. So they can be obtained from like compromised websites or advertisements, basically to get you to click to download it. Spyware is particularly concerning. It's used to obtain information and profit from a user. It records information about your computer use and sends it to an attacker. So this can be like any number of things, but usually passwords, emails, payment methods, etc. Rootkits are a stealthy form of malware, so depending on their author, they can be almost impossible to remove. Rootkits take hold of a computer at a security level equal to or greater than the user, so they're well beyond the user's privilege to remove them. And it also prevents normal antivirus from removing them. So they might embed themselves in like the firmware of your computer, and a reinstall of like the operating system won't fix the problem in that case. They can take months to years to develop. This is why they're usually attributed to like government agencies and other APTs or advanced persistent threats that have the resources to develop these. And they can be detected out of band by analyzing the computer's hard drive on another computer, but you can only really do this by comparing a clean copy of a system to the contaminated one. Botnet is a group of individual devices under control of an attacker, so they act in unison to receive commands and perform actions. And so they do things like denial of service attacks or cryptocurrency mining. And the denial of service attack basically means they overwhelm a server and make it inaccessible. These are actually sold as a service sometimes, meaning criminals can buy subscriptions to them and carry out malicious attacks for a monthly fee. A botnet called Mirai was responsible for taking out much of the services for most of the East Coast in 2016 by using millions of poorly secured Internet of Things devices. So it generated around, I think it was like 620 gigabytes of traffic, and decided to specifically target one security researcher, which took his website offline for most of the day. Ransomware encrypts your data and demands payment for it. So this is usually in Bitcoin. And although sometimes the encryption method is pretty poor or badly implemented, and researchers can decrypt the data for free. But a variant of ransomware called WannaCry, you might remember, took over several companies and millions of users' computers in 2017, using a vulnerability stolen from the National Security Agency. And finally, a backdoor isn't really malware, but it's used to circumvent standard authentication methods. So it would be malware if used with ill intent. And it usually provides administrative or like system level access to a system. Now that we've covered the types of malware, we want to talk about like how do we detect these. And so an older but still used and still rather common method of detection is via signatures. Signatures are strings of text or code containing an executable file that's like unique to that malware. So an antivirus program compares each file in a system to its database of signatures, and if there's a match, it quarantines the file. However, this method of analysis isn't really adequate anymore. We now have malware that can change its internal code structure with each replication to avoid detection, which is known as polymorphism. Metamorphism is similar, but it's more about anti-analysis. It adds a bunch of junk and changes the order of instructions to make it hard to analyze or detect. And packing compresses an executable file so that like signature-based analysis like this is typically ineffective against it. But there are some ways around that. We're just not very good at it yet. Behavioral malware detection depends on execution. So researchers or antivirus programs execute malware in a sandbox or a virtualized safe computer where the malware can't escape, and observe the effects and then reset the sandbox to what it was originally so they can continue analyzing more malware. This is pretty effective unless you have a security issue with your sandbox and the malware is sophisticated enough to escape it, which again is usually only governments and other very expensive threats can have this capability, but it's something to keep in mind. Behavioral detection can also detect like zero-day or unknown malware just by looking at malicious actions rather than looking for a specific malicious known program. However, as mentioned previously, some sophisticated malware can detect sandboxes and take adverse action, so like shutting down or acting like it's not bad software, and that's known as context-aware malware, and it's difficult to analyze when done properly. More recently, anti-malware researchers and corporations have been applying machine learning to malware detection. So in case you all don't know what machine learning is, it allows computers to learn from data and build models to further identify that type of data without human intervention. There are a range of methods for training machine learning algorithms, but the two most common are supervised, where a researcher monitors and adjusts the learning process, and unsupervised, where the algorithm mostly is allowed to learn by itself. Malware detection usually uses supervised learning, so it's supplied with benign and malicious software based on various features of programs and learns to tell the difference between the two. Static analysis via machine learning is done by like analyzing an executable file itself, and dynamic analysis is done by actually executing that file and learning from what the binary then does. So these are some of the features that machine learning algorithms can be trained on to detect malware. Static sequences that don't change are like strings or bytes. So if a malware has like a hard-coded URL in it, that can sometimes be used. Opcodes, which are instructions of the instructions that are used to tell the program what to do. There are certain ones that you never generally see in benign software, and it's really easy to like call it, hey, that looks like something malicious if it's using that particular opcode. Sometimes even the way the program is structured, like if it's aggressively trying to use a lot of obfuscation techniques or confuse the malware researcher, that's pretty suspicious because usually most developers don't care if their program is reverse engineered or analyzed. And when the data about how the program was compiled, that's called metadata. So that's things like what compiler the program used, when it was compiled, who it was compiled by, what country and language settings, etc. Sometimes the style of an executable can actually be used to identify the author in this way. And some malware authors actually know this and intentionally write their code to look like other authors. I believe North Korea uses that quite a bit in some of the malware that they release. They try to attribute it to Russia or China. So dynamic features use actions like calling application programming interfaces, which are ways to interact with other programs in the operating system. They could modify the registry, which is an important part of Windows functionality, or by modifying system calls or files to like add instructions to do other actions. The last thing you need to know is classification terminology for malware detection. A true positive sample is malware and is classified as malware, and a true negative where a sample is not malware and it's not classified as malware. Those are the ideal situation. We always desire to have those happen, but occasionally in research, we do get a lot of false positives where a sample is not malware, but it does something to make it classified as malware, and a false negative. This is generally the worst kind where a sample is malware, but it's not classified as malware. Now that you're aware of how malware is detected and analyzed, these are some of the challenges I'm attempting to address with this paper. So my paper is called Prudent Practices 2. It's a continuation that I already mentioned that analyzes academic research papers from various conferences and assesses their accuracy and research methods. So this is based on 2 or 3 papers of previous work. The main one would be the original Prudent Practices paper. So it was presented in 2012 at the IEEE Symposium on Security and Privacy, which is one of the probably the most prestigious academic malware conference that occurs currently. And it examines the experimental methodology and rigor of malware publications from around 36 different papers in top tier venues like Security and Privacy, or what's also called S&P. So like S&P and other venues like Unix Security. And it developed the criteria that I updated to perform my analysis in 2020. There are two other papers that I thought were important to mention here. The first one is Be Sensitive to Your Errors, which applies the criteria from the 2012 paper to develop a new automated malware classification system. And this helps control the false positive rates of most modern antivirus scanners and offers a great deal of flexibility in adjusting for errors, which is really helpful when you're trying to analyze the prudence of various academic papers, and they're all using different techniques for identifying malware. And finally, Helping Johnny to Analyze Malware, which where the authors created an add-on for popular decompilation programs such as IDA Pro and Dream that improved the comprehensibility of their output and made the analysis more accessible to people who are not as experienced in malware analysis like me. So I began my research by modernizing the criteria used in the 2012 paper and selecting 35 new papers to analyze for their prudence. The three criteria I chose to focus on were machine learning, sandboxes, and mobile malware analysis. So machine learning really wasn't a thing applied to malware in 2012, or at least it was still emerging, and therefore it wasn't assessed in the original paper, but it's rather important now. Sandboxes ensure the safety of the researcher, as I previously mentioned, and context-aware malware is a bit more prevalent since this method of analysis has grown in popularity while signature-based analysis has kind of declined. And finally, mobile device usage since 2012 has skyrocketed, and the original research lacks any applicability to devices that were non-desktop. So I selected my papers from 11 different conferences, 3 of them which were considered highly selective top-tier conferences. I go over my criteria more in the actual paper, and I chose most of my papers from them. I broke down my research into 2 different categories based on either first or second and third tier papers, and I assessed the prudence of all of them together, and then just the top tier conferences to see if there's any difference between their selectiveness levels. This chart is of the papers I analyzed per conference and year. I stuck with ranges of 2014 to 2019 so that I could find more research related to the goals I was interested in. Most of the research is from 2016 and from a conference called the Network and Distributed Systems Security Symposium, so NDSS, and is balanced similarly to the original paper so that I could get the most accurate comparison of what has changed in these 8 years. After I had my goals and papers selected, I needed to establish a criteria to analyze them and determine how prudent each paper actually was. So I created and modified many evaluation criteria, which we'll discuss in a minute, that I believed represented prudent data practices in malware analysis. And some of these were included in the original study published in 2012, and others I added to cover the goals that I outlined for this project. I used the same 3-level qualitative importance rating for each criteria that the original authors did, indicating which were essential for accurate research, filled circle, just recommended, half circle, or optional but beneficial to the reader, which is an unfilled circle. I also, in doing this, I found that I had to modify the rating system of some of the original criteria as they were no longer accurate or as relevant in 2020 as they were in 2012. So this would be, say, things specific to a certain outdated operating system, or malware that is sinkled and no longer is active or exists, etc. The rating system allows weighing the interpretation of the survey results according to the criteria's criticality levels. I evaluated each paper using a rubric that I created, and I rated them as correct or incorrect as they adhered to each criteria. I recorded the results, so the number of applicable papers to that criteria, and then of those applicable papers, the percentage of them that performed the criteria correctly. But not all papers used every criteria, so it's important to note that those that didn't use the criteria, I didn't count them as part of the score for that criteria. If there was a paper where I couldn't tell if the criteria was applied or not, I listed it as unknown, and I included it in my results as well. So now I had a very large amount of data to evaluate. And these are the categories that I sorted my criteria in to evaluate each paper. So the first category is correct data sets, which ensures that the authors properly, say, cleaned dead malware samples from their data. If something no longer functions because it's missing the server it communicates to, you don't need to analyze that. It's not going to give you useful information. Specified their machine learning benchmark. So what data did they use? What training method did they use? Is the data publicly accessible? Can other people go train machine learning algorithms on it? Whether or not they balance their samples over many different types of malware, or if they stuck to one single malware family, etc. In the center, you can see the guideline that each criteria pertains to in my paper. I didn't include the full list of guidelines here because they would take a very long time to go over, but they will be available at the end if you'd like. And I did include a brief description of what I'm looking for on the right side to supplement for this. The importance is also included, so how important I thought each criterion was to prudent research practices. The second category we have is transparency, which is ensuring that the authors interpret their true positives and false positives and negatives accurately. So it's good to explain these. As machine learning. I mean, as I've experienced, I'm sure some of you who have worked with it experience, it can be quite a black box. It's hard to tell how it's exactly learning. So the reason why something was classified a certain way is a good thing to mention, or at least try to explain for the reader. And they also need to list various criteria to allow others to reproduce the experiments. This is the basis of any scientific study. So basically malware families and names so that other people can go download them and use them for their research. Criteria for retraining, if you have to retrain a model because it becomes inaccurate after so long, or especially the operating system and the environment used. If you don't know how somebody set up their lab, you don't know how to really replicate that and perform an accurate experiment based on their research. And finally, realism and safety. So researchers here should remove outdated or sinkled samples that would invalidate the experiment, allow contained internet access, emphasis on contained, or evaluate on multiple operating systems, and or add user interaction in case a malware is smart enough to detect when a user is not running, or you have a malware that only activates when a specific user action is created. So for safety, the researchers should deploy containment and describe how they deployed their containment. Doing so protects other researchers who may want to reproduce the experiment without having to guess how to do it safely. So now we can actually discuss the results. Of the essential criteria analyzed, so those were indicated with the filled circle, 9 of them increased in accuracy and 1 of them decreased. So these results are generally, as you can see on the table at the right, where it talks about the average paper rating per each rating that was received. There's been a lot of progress because especially for 8 years, getting a whole industry to change about getting a 10% better score in adequacy for each criteria outlined, and significantly reducing the number of unknown criteria, or where I'm not able to figure out what was happening, as opposed to 2012, is definitely progress made in the industry. It takes a while for any industry to change, so this looks really good so far. For the recommended criteria, this has improved as well. It hasn't improved as much, but it still has improved, and we've made a significant reduction in the number of unknown attributes that I had to assign. So 9 of the 13 I was looking for, 9 of the 12 I was looking for in accuracy increased here, and that's good. And then 3 of them decreased. So the specification of environments and operating systems decreased. That's probably due to because we have so much malware now, and there's a lot of malware that is on different platforms. We use an emulator that can emulate many different platforms at the same time. So with the increased use of emulators and virtual machines and all-in-one sandboxes, malware platforms and malware analysis is becoming more agnostic, so it might not be as necessary to specify these anymore. But I would have to do more research on that to determine it. So finally, the optional criteria was really interesting because several of the erroneous practices actually increased here. So the introduction of newer technologies like machine learning and robust sandboxes, they might reduce the need for some of these criteria, like mentioning trace duration or added user interaction, because the sandbox now can effectively emulate a user well enough that you don't need to actually add a user in there. And it might not be necessary to record how long the malware is executing, because when we have polymorphic malware that can change, the execution time might change across different platforms as well. And it's harder to predict those sort of categories. So they might not be as present in malware or in malware research in the future. But right now I was still checking for them, and they definitely did decrease, which I thought was interesting. And finally, so basically, malware analysis, as we see in my research, has advanced in sophistication and accuracy since 2012, and that's really a good thing. A lot of the important criteria that I looked at, I saw increase. So the data selection, specifically like selecting sources, properly selecting your sources, and then understanding like where your data is coming from, what data that contains. That was kind of an issue in 2012 because malware researchers would just go out to large sites such as VirusTroll is a common one to download samples, and sometimes you could get actual malware, sometimes you can get something that is not malware, sometimes you can get even a non-executable file, and that has definitely improved since 2012. So it's a good thing that we are selecting our sources more properly. Data cleaning as well, so removing samples that don't longer work or are sinkholed or inactive or don't run on a certain operating system that's relevant anymore. That has improved as well. And program training, so especially with the introduction of machine learning, has been a real help for this category. Training and retraining criteria are typically specified, and it really helps when this is specified so that other people can conduct your experiment. Excuse me. And then malware learning methods, or machine learning methods, sorry. So machine learning methods have also just kind of really grown in prevalence for both program training and experimental evaluation methods so that we can perform things like cross-platform analyses and understand how a malware might grow or change over time or populate itself across a certain area of the world over time. And that has really been a boon for the industry in helping us determine things like that. And finally, at least I thought it would be rather obvious that you should specify what containment and safety practices you're using when you're analyzing malware. And I was really surprised to learn that a lot of research in 2012 didn't do that. So it was interesting to learn that, and I'm really happy to see that this was an increase in between that 8-year time period. But also, sandbox technology has become a lot better and a lot more reliable since 2012, so that probably has a hand to play with it. I just want to point out in the conclusion that there will never be an objective set of criteria for proper malware analysis. New malware and malware detection techniques are always coming out, and researchers are always coming up with new methods to detect malware, while malware authors are always coming up with new methods to avoid detection. So both sides of the effort are continuously growing more complex and harder to understand, and this field is getting pretty complicated pretty fast. And for people trying to break into the industry like me, understanding and having a proper way to analyze malware consistently and read other researchers' papers that have consistent techniques applied as well is really helpful. And revisions regarding transparency, realism, correctness, safety, so basically much everything I did, it'll be valid for a few years, but there will never be a perfect or completely current set of guidelines. New techniques will emerge, and they must all be reframed again, just like any other industry. So I believe that's the last slide. Yes. I just want to say thank you all. This class was fun and a topic I really enjoyed. So thanks for listening. Is there any questions?